ஒரு So 2 of you are there. We'll wait for 2-3 more minutes. Let your friends join. Five, 2 of you. Is the school going on for you guys?
Oh, yes, sir.
Okay. So I think the school gets around 5 o'clock, 4:45, something like that.
Yes, sir.
Actually, it's like half day, sir.
Oh, half a day only. Okay. That's why I don't see people. Okay, fine. Maybe we'll get started. Maybe they'll join later. Okay, I think I don't know the names, the 2 names which I see are little new to me. I don't think I have taken classes for you. Have I?
No, sir.
No,
I have
sir.
just enrolled for the test series.
Yes.
Oh,
Same,
understood.
sir.
Understood. Cool. No issues. Fine. So today, according to the schedule, we have to see 2 chapters. That is haloalkanes, haloarenes, and alcohol ethers phenols. Is that right? Is that what is given in the schedule for you?
Yes, sir.
Sir, it's only haloalkanes.
Oh, it's only
Yeah.
haloalkanes and haloarenes.
Yes, sir. It's only
Yes, sir.
Cool. Then chill. Then it is a little more easier for us. Okay, cool. So we'll start. So guys, rather than me teaching you something, right? So what we'll do is we will try to solve some questions that will actually be that will actually make sense. How many ever times actually you will teach when it comes to answering questions? That's where the problem lies with respect to exams, isn't it? Okay. So we'll start. I'll just give you some questions. One. And obviously, you can ask me whatever doubts you have. Like, do you have anything in specific in this chapter you want me to teach? Guys?
So probably the mechanism once, if you could.
Mechanism of SN1, SN2?
Yes, sir.
Okay, so fine. First, we'll see that. Then maybe we'll continue with the question. Fine. Cool. So if I start, say, with SN2 mechanism, right? Fine. So as the name, we know what is it. It is going to be nucleophilic substitution reactions, right? So nucleophilic substitution nucleophilic substitution reactions can happen in different pathways, right? 2 of them are actually going to be SN2 and SN1, right? There is another in Kfetol, you have phenyl rings and stuff. Then you have something called as SNAR, that is nucleophilic substitution at aryl compounds, and you even have something called as benzyne mechanism, right? So anyways, the most I'll say the pathways mostly taken are going to be this SN2 and SN1, right? Okay, so what does this 2 represent, right? This 2 represents that it is going to be a bimolecular reaction, right? The 2 represents that it is going to be a bimolecular reaction. So I think you have studied chemical kinetics, right? So it's all about, so obviously you're going to see that I'm going to have an alkyl halide or any substrate. This is my substrate, right? So this substrate will react with the nucleophile to form R nucleophile plus X minus. As simple as that, right? A substitution reaction. One nucleophile, X is a nucleophile, another nucleophile, incoming nucleophile will replace it in the product. That's how it happens. Anyways, so now if you look at these kind of reactions, right? So if I write the rate law R, we know how to write the rate law. Rate law is equal to K into A power X into B power Y, where A and B are the reactant molecules, right? So here you see there are 2 reactants, that is Rx and the new incoming nucleophile, right? So if I say it's bimolecular, okay, now I want to tell something here. When I go to kinetics, right, now there are 2 kinds of reactions you can see, right? One are what are called as elementary chemical reactions, and the other one are what are called as complex chemical reactions, right? So please understand, when I say elementary or when I say simple, elementary or simple, both are same. When I say elementary reactions, they are going to happen in single step, right? Single step process, right? So those are what are called as elementary reactions. Now, when I go for complex reactions will have more than one simple step. Basically, they're going to be made up of many number of simple steps, right? Elementary steps, right? So complex reactions are made up of so many number of elementary steps. Okay, so anyways, now when we're going to the elementary steps, elementary reactions, right? Now there the molecularity and the order of the reaction can be same. We know what is molecularity. Molecularity is basically the number of reacting molecules. I hope all this you should have been there. That's why I'm little going fast. So you know that molecularity means the number of reacting molecules, right? So if it's an elementary chemical reaction, right, the molecularity and the order of the reaction is same, right? So now assume that this is an elementary reaction. This is an elementary single step process, right? Now they say it's bimolecular, and you see there are 2 reactants. The molecularity of the reaction is 2. One of this, it's 2. The order is also going to be 2. Anyway, so how do you write it? It will be K into Rx power 1 into nucleophile power 1. So that is why you see 1 plus 1 becomes 2. That's why it is going to be called as bimolecular. What do you mean by this? The rate of the reaction, the rate of an SN2 reaction is dependent on both the substrate as well as the nucleophile. That's what you need to understand here, right? If you change the concentration of this, or if you change the concentration of this, or if you change the nucleophile, anything, whatever it is, you will see that the rate of this reaction is going to be changing. Okay, fine. Now we'll look into what exactly is the mechanism, right? Now it's pretty simple. Now what you have to understand, it is going to be a single step process, right? It is going to be a single step reaction, right? Okay, so what is going to happen is something like this. I write Rx, right? Now you have the incoming nucleophile coming, right? Now what is going to happen is this nucleophile is going to attack the carbon from the other side, from where I had the nucleophile, where I had the halide X. Why? Because of repulsion, is it not? If it is going to attack from the same side like this, if it's going to attack from this side only, right, you will see that this already has so many number of lone pairs of electrons. There is already a bond pair present, right? So you will see that actually there are so much amount of repulsions between the electrons will happen. So to avoid that, the nucleophile will prefer to attack the carbon atom or to attack the alkyl substrate from the backside. Okay, right. So when this is going to come near this, right, so you are going to see this kind of thing happening. You will see that I represent this bond by a dotted line and another bond between the R and the nucleophile as a dotted line. Okay, so what do you mean by this? Is this is what is my intermediate, or I would say this is my transition state, TS. Okay, TS represents transition state. So generally in your NCERT textbook, maybe they would have given in terms of CH3X, right? So they would have, anyways, instead of this R, you just have to put a C and put 3 more hydrogens, and then to make the same thing. Okay, so anyways, so this is the transition state. So what do you mean by this is, you see there are going to be 2 things happening. One is that the Rx, that is the CX bond is breaking. Simultaneously, the C nucleophile bond is getting formed, right? So bond breaking, that is the bond breaking between the C and X, and the bond formation, that is between C and the nucleophile, new nucleophile, is happening simultaneously. Okay, now that this is how you represent it. This bond, as this bond cleaves, this bond gets formed. Right now, this process will continue. This bond will cleave more and more and more. This bond will form more and more and more. And at the end, you will see that the R or C nucleophile bond is completely formed, and the CX bond is completely broken. Right? So you see, this is a single step. Now you can see, sir, this is a double step process. You can ask me, sir, what is this? This is the step, isn't it? You see that the intermediate transition state is getting formed is really not that stable. This is just a hypothesis which is given just for us to understand that this is what is going to happen. Okay, so basically what you see is this comes in and this comes out single step. This reaction is going to get over. Is it okay? Right. So this is what is SN2 mechanism. Now, what are the other things we have to know? One thing is about the kinetics. That is going to be a second order or bimolecular reaction. The rate depends on both the alkyl halide as well as the nucleophile, and you have to know the mechanism. This is the mechanism, right? Now, what other stuff? Now, the question is, you have other mechanism SN1 also. Now, what kind of substrates? When I say substrate, alkyl halides, right? So what kind of substrates will undergo SN1? What kind will undergo SN2? What are the conditions, reaction conditions which will favor SN2? What are the reaction conditions which will favor SN1? All these things also you have to, right? So fine. So if you look into it, right, say if, now I'll have to rub this little part, right? Say I compare H, H, and a H, and I have the X, and say I have a tertiary butyl group and X. Okay, now I'm going to compare these reactivities with respect to SN2 mechanism, right? Okay, now what you see here is this carbon atom is attached to 3 hydrogen atoms, and this carbon atom is attached to 3 carbon atoms, to 3 methyl groups. Right. So now you understand that the nucleophile has to attack the carbon atom which is from the side which is opposite to the side of the halide. Right. That means what I have to understand, the nucleophile, if I have, it will attack from this side, because this side only I have the leaving group. Leaving group is the halide. Right. And in this case, it has to attack from this side because the halide is this side, isn't it? Right. Now, don't you logically see that there are only 3 hydrogen atoms? This nucleophile can easily attack here, but here I have 3 bulky methyl groups, right? So the nucleophile will find it little difficult to go and attack this particular carbon atom from the backside. Okay. So what you have to understand is the reactivity of the substrate, reactivity of the alkyl halide is inversely proportional to the steric hindrance. Steric hindrance is bulkiness. Okay, more and more bulky that substrate is, more and more difficult it is for it to undergo SN2 reaction. Right? Okay, so keeping this in mind, now we know that we have 3 kinds of alkyl halides, like say normally we say primary, secondary, and tertiary halides. Right, so I obviously know tertiary halides are going to be more bulkier than secondary halides, than primary halides. So if I look into the order of reactivity, right, the order of reactivity, you will see that the primary halides which are least bulkier are going to be most reactive, and the tertiary halides which are maximum bulkier will undergo the slowest reaction with respect to SN2. Okay, right, fine. So that is about the reactivity. Now, what other stuff? The last thing you have to understand is what kind of solvent, right? What kind of solvent or what kind of reaction conditions will will help or will make SN2 more probable, right? So the only thing you have to understand is you have to use a polar aprotic solvent, right? Okay. So what do you mean by this? Polar. So you know what is polar? Polar is something like a AB bond, right? When I say a polar bond, right, AB bond, which is having high electronegativity difference between the bonding atoms. Say for example, HCl. If I take chlorine is highly electronegative, hydrogen is highly electropositive, right? So there is a huge difference in electronegativity between the bonding atoms. So because of that, what is going to happen? Because of that, you will see that whichever is more electronegative, the electron cloud is going to be more towards that particular atom. More and more electronegativity, more electron pulling power, right? So that will induce a partial negative charge. If I put del minus, it represents a partial negative charge. And since the electron cloud is moving away from whatever the atom it is, more electropositive atom, right? So that will get a partial positive charge, right? Okay. Anyways, so these are these kind of bonds, if they exist in a compound, right? Those kind of compounds are what are called as polar molecules or polar compounds. Say H2O, HCl, HF, ammonia. All these things are the examples. Okay, fine. What do you mean by aprotic? Protic means anything which will give me H plus ions. Say water is a very good example. It doesn't give me exactly H plus, but still the OH bond is little polar, so it can be. You would have seen so many reactions where from H2O H plus can be gotten if I have very strong bases and stuff, right? So protic solvent, right? Alcohol is a protic solvent. Again, it can give me H plus, right? So a protic solvent is one which will give me H plus, and aprotic solvent is the opposite, which should not have any acidic hydrogens. Little acidic also is not. It should not be there. Those are what are called as aprotic solvent. Okay, so this condition, polar aprotic solvent, will enhance the probability of the substrates to undergo SN2 reaction. Is it okay? Right? This is about SN2. Any doubts about SN2? Is it clear? Yes? No? Are you there? Okay, fine. Everybody. Oh, now there are so many people. Oh my God, where did you guys come from? I started there only 2 people. Okay. So, anyways, so this is about your SN2 mechanism. Okay, right? So, people who have joined late, if you have missed something, please watch the first 5 minutes of the recorded video, which will be given to you. Okay, right? Fine. So that is about SN2. So now we'll see SN1, right? Okay. Now, if at all I were you, I would have asked one question. The thing, why is it that the polar aprotic solvents help in SN2 mechanism? I would have asked the question, right? Now, the answer to the question is that any polar aprotic solvent, right? Any polar, okay, examples first you have to understand. Example can be DCM, dichloromethane. Dichloromethane is very simple, CH2Cl2. Right? Or I can even use CHCl3, chloroform, right? Or there's something called as DMSO, dimethyl sulfoxide. Like so many are there. Okay. So what you have to understand is what is the role of these in the SN2 mechanism? They're going to stabilize the transition state. We saw about the transition state when the simultaneous bond breaking and bond formation happens. That particular transition state is little stabilized by these kind of solvents. Okay. Now, how they're getting stabilized? It is too much for our level of chemistry, right? Maybe if you go to higher levels of chemistry, say takes BSc, maybe you'll understand, right? Okay, cool. So that's about SN2. Next is SN1 mechanism, right? In SN1, as the name tells you, again, it's substitution, nucleophilic, and this one represents its unimolecular reactions. That means, again, all are elementary steps. They're not complex reactions, right? That means what? The order of the reaction is 1. Okay, unimolecular means the order and molecularity are same for elementary steps, right? So here the order is 1 and molecularity is also 1. Okay, fine. Now next, that means if I in this case also I have 2 stuff. That is 2 reactants. You have the Rx, you have the nucleophile, right? But still I say that the order is 1, right? Fine. Now how can the order be 1? Can you tell me? What are the possibilities you can think of?
Sir, only the reactant will be reacting, like it's a
Which
one
reactant?
step.
Both are reactants, right?
Sir, I didn't get.
You said only one react. You said something. What did you say?
Sir,
What did you say?
only the reactant part will be like reacting in the first step.
What do you mean
Like,
by only the reactant part? This is the reactant. This is also the reactant. Which reactant?
so not the nucleophile, sir.
Okay, I understand. Right, and that is correct. Right. So that is what is exactly happening. Now, if you think of any other possibility, right? So any other possibility you can think, I can write R is equal to K into Rx power half and nucleophile power half. Again, you see the order is 1. Right? But again, this is not going to happen. Right? Now, how do you prove it? Now, we know the actual rate law. This is wrong. The actual rate law is Rx power 1. This is what is the actual rate law. How do I confirm this? Any idea? Let me see how much chemical kinetics you know. Let me see that.
Actually, we can use a nucleophile for the power 0 also, sir. Rx to the power 1 and
Correct. Nucleophile power 0. Correct. I
yes.
understand. Right. So what do you mean by this is the rate depends on the concentration of the alkyl halide and it doesn't depend on the concentration of the nucleophile. That's what it means, right? How do you prove it is what I'm asking.
So the rate determining step is the breaking of alkyl halide.
See, one thing I'll tell you, okay? So not only this mechanism, there are, for every reaction, there's a mechanism. And what you have learned in NCRT is not even, I don't know, 0.1% of organic reactions are there. Those are the basic level reactions, right? So for whatever be the mechanism, those are all theoretical predictions. Okay, those are actually theoretical predictions. With the help of some amount of experimental setup, I'll be able to predict the mechanism. We really don't know that's exactly what is happening, but we'll be able to give supporting information that, yeah, okay, this might be the mechanism, right? So with respect to the mechanism, basically, this is experimentally obtained. Okay, whatever the rate law, the orders, and all these stuff are actually experimentally obtained. And based on this, I can give the mechanism, not the other way around. Based on the mechanism, I give the rate law. No, it's not like that. Right. So you must have learned about how do you determine the order. You must have read some methods by which you'll be able to determine the order of the reaction. Right. So for example, right, I have R, that is the rate of the reaction with respect to the concentration of Rx. Okay, right? Now, tell me, looking at this particular equation, tell me how the graph will look. Look at the equation and say, tell me how the graph will look. R is here, K, and this is not there, right? This is only there. How will the graph look?
Straight line, sir.
Correct, straight line. Any other information about the straight line? From where to start? Something like that. Positive slope, negative slope.
Positive
See, look at
slope.
this. See, this is y. R is in y. This k is m, and this is the x-axis, isn't it? So this is like y is equal to mx. Y is equal to mx. It doesn't have any intercept. No c is there. So obviously, it has to start from the origin. And you see, m is positive, so it is going to have a positive slope. You are going to have a straight line. Okay, right. Now, if I plot a graph between R and the nucleophile concentration, now tell me, okay, now forget about this, we'll go for SN2, previously what we saw, right? So in that case, you saw Rx power 1. So this graph is correct, right? Now, again, if it was SN2, you will get the same graph with respect to the nucleophile if it is SN2, because again, nucleophile power 1 was there in SN2. Correct. This is for SN2. Right. Now, tell me how the graph will look for this R with respect to this. How will be the graph? How will be the, whatever, right? If it's a straight line, how is the straight line? How will be the graph for SN1?
Sir, is it parallel to the x-axis? The straight line is parallel to the x-axis.
Absolutely, absolutely. right? What do you see? The rate is independent of the concentration of the nucleophile. It doesn't depend on. So whatever be the rate, that rate will stay. So this straight line represents SN1 mechanism, right? For both SN1 and SN2, this graph stays good, because in both the cases Rx power 1 is there in the rate law. But in this, right, you see that the SN1 mechanism will have a straight line parallel to X-axis because it is independent of the concentration of the nucleophile. But with respect to XSN2, you will have a straight line with respect to the nucleophile concentration. Okay, this is all you must have studied, isn't it? You know how the graph looks for a zeroth order reaction. You know how the graph looks for a first order reaction, right? Anyways, cool. So too much about kinetics, right? So okay, so we understood that this is what is the rate law. Okay, that is Rx power 1 and nucleophile power 0 is what we understood. Okay, fine. Now next thing what you have to understand, it is a two-step process, right? Last time it was one-step process, here it is a two-step process, right? So here what do you see? First you have the Rx, right? Now first thing what happens is the X minus leaves. See, the arrow shooting is very important, guys, right? And with us, you have only very few mechanisms in your textbook in NCRT, right? So for those mechanisms, the arrow shooting is very, very important, right? So what I mean by this arrow is this lone pair, this bond pair, I have two electrons here, right? Now these two electrons are taken up by X is what you have to understand, right? So X, this X is not only taking its own electron, but it is also taking the electron that is coming from the carbon. So obviously that is why I'll have a negative charge, and the carbon is losing the electron, so that will have a positive charge, right? So what will you see is R plus X minus. So here, this is the first step, right? So first step is formation of carbocation. The X minus leaves, right? Leaves the carbocation to be there. Okay, fine. So the carbocation is formed, and then the second step would be the nucleophile attacking the R plus. Now see, again, arrow shooting is very important. I am not putting R plus attacking the nucleophile. I always put nucleophile attacking the positive center. Not only in this reaction, in whatever be the reaction, the electrophile should not move. The nucleophile is all one which will move and go and attack the electrophile. Electrophile is one which is having positive charge, right? So electrophile is here, the nucleophile will move and attack the carbon center, which is having a positive charge, right? And that's it. The last step would be the formation of the bond, R and U, the nucleophile. So this is the second step, right? This is the second step. Okay. Now, this is a complex reaction, isn't it? Because it is made up of more than one elementary step. First step is an elementary step, formation of carbocation. Second step, the addition of the nucleophile to the carbocation is the second step. That is the elementary step again. Right. Now, whenever you have a complex reaction, right, there is always a thing called as rate determining step. If you have more than one elementary step, you have to know what is the rate determining step. Right now, what is rate determining step? What do you mean by rate determining step? It is the slowest step. We already know that, isn't it? It is the slowest step among the number of steps. Whichever happens the slowest, that is what is going to determine the rate of the reaction. Right. So you see, what you have to understand is the first step is the rate determining. That is the formation of the carbocation is the rate determining step. So among the first step and the second step, first step occurs very slow compared to the second step. So that is why you see the first step is the rate determining step, right? Now the kinetics, that is the rate law, which you see R is equal to K into R power X. Someone must try to explain with this only, isn't it? Like with respect to the mechanism. You see, if this is the first step, you have only one reactant here, right? And the reactant is Rx, right? Nucleophile does not even come into the picture because it is not in the rate determining step, right? That is why in the overall rate law, right, you don't see the nucleophile coming, right? Anyways, this is not the way to explain. Use this. Actually, this comes from this. That's what I understand. Okay, fine, cool. So that is about the SN1 mechanism. So two steps: formation of carbocation. Second step is to be the addition of the nucleophile. Now, next thing is again you have to look at the reactivity, right? Now there, the reactivity was only based on only one thing, that is steric interest, crowdedness. More and more crowdedness, less and less was the reactivity. Right? Now here, you see there's a special thing happening. The special thing is the formation of the carbocation. Right? Now formation of carbocation. So what you have to understand is, in this case, the reactivity is directly proportional to the stability of the carbocation. C plus represents carbocation. Okay, the reactivity is directly proportional to the stability of the carbocation. More and more the stable the carbocation is formed, more and more will be the reactivity of this substrate Rx. Again, we know we have primary, secondary, and tertiary carbocations. Right? Now we know tertiary is more stable than secondary. I'll come to that. Right? I'll ask you the question. So we know the order of reactivity is going to be the same as the order of stability of the carbocation. So the order of reactivity in this case is exactly ulta of what we saw for SN2, that is tertiary is more reactive than secondary, secondary is more reactive than primary, because tertiary carbocation is more stable than secondary, which is more stable than a primary carbocation, and which is more stable than a methyl carbocation. Right? Okay. Cool. Now this is about the reactivity. And last thing, right? What favors SN1? What kind of reaction condition favors SN1? And that is exactly opposite of SN2. Here in this case, we have to see that it is going to be a polar protic solvent, which will favor. That is like H2O, ethanol, any alcohol is fine, right? Fine. So a polar protic solvent will favor it. Again, why? Because it stabilizes the carbocation. With the help of hydrogen bonds. You don't have to go into the details, right? So what you have to understand is the protic solvent, right, stabilizes the carbocation form with the help of hydrogen bonds. That's why we have to use a polar protic solvent. Okay. Now tell me, guys, I want to know why, or say include this also. Why is this the order of stability of carbocations?
So because CH3 in tertiary carbocation, it's a electron donating group, so the proton will be stabilized faster.
Okay, makes sense. So guys, what you have to understand is there are actually two ways of explaining this. Okay, so the two ways of explaining, say now with respect to inductive effect, we'll be able to explain it. As you said, the Umar told it. So you see, I have carbon to have a positive charge. Right. Now, what you have to understand in organic chemistry is more and more neutral the species is, more and more stability. That means less and less charge which is present on the particular compound, more and more is the stability. Obviously, right? Most charged species are unstable, neutral species are stable. Correct. Right. So what you have to understand is if I have just CH3 and if I have say one CH3 with two H2s with a positive charge, I say I go for tertiary one. That is, this is primary. Okay, I'm not writing secondary because it's going to be understood, right? Okay, so again, there's a positive charge. Okay, so what you have to understand is the alkyl groups, the CH3s you see here, are electron donating groups. EDG means electron donating groups. That means they're going to donate electron to this carbon center, the positive center. This is going to donate. Okay, so if they donate electrons, electrons are negatively charged, right? For carbon atom here is positively charged, so they will decrease the positive charge on the carbon atom. Okay, so that's what I said, lesser charge, more stability. Now the amount of positive charge on the carbon is decreasing because of the electron donating effect of CH3, right? It is getting stabilized. That is why we see this order. The tertiary will have 3 alkyl groups, secondary will have only 2 alkyl groups. This is primary, here is having only 1 alkyl group, and CH3 plus doesn't have any alkyl, right? So maximum positive charge, minimum positive charge, minimum stability, maximum stability. That's it. Okay, so that is with respect to inductive effect. There is one more way I think I'll be able to explain this. Can you tell me what effect was that? It's all from 11th class, but still, what effect was that? Nobody remembers. Some of you might be going for JE exams, and you must have been wrote it now. You must have studied for 11th and 12th. What is the other effect?
So the resonance.
No, resonance will happen if I have pi bonds or pi electrons. Here I don't see any pi electrons. The other one is actually, okay, I don't have space. It is hyperconjugation, right? I don't want to go to details again. It will take another half an hour for me to explain what exactly hyperconjugation is, right? So anyways, there are two ways of explaining. Either way, you get the same thing. Tertiary greater than secondary greater than primary. That's what you get. Okay, right? Fine. So that is about your SN1 and SN2. Okay, I think detailedly we spoke, right? Anything else from this chapter, guys? Anything specific from this chapter you want to know? You want me to teach? Okay, fine. Then we'll go for some questions. Oh, and I forgot one most important thing. In SN1, SN2, what did I forget? Tell me. I forgot something. SN1 and SN2. What did I forget? Is everything, whatever is there in your book, taught here?
Optical activity.
Sorry?
The optical activity.
Correct. This is stereochemistry part, right? How the stereochemistry is changing when I have SN1 and SN2, that we have to see. So that we'll see now. Okay. Okay. Say consider SN2. Okay, first we'll take SN2, right? Now assume that the Rx, which we write, is chiral. We know what is chiral, right? Chiral means all the four groups attached to the carbon atom is different. That is what is meant by a chiral center or chiral carbon atom, right? Okay, so if I have a chiral center which is marked by a star, right? Say assume that I have some I have some A, I have some B, okay, I have some B, say I have some C, and you have, or I'll write it like this, right? I have some X is what is the nucleophile. I mean, X is the leaving group. Okay, and you have some C. Okay, right? I have this present. Now you see this is chiral. How is it chiral? A, B, C, X, all four are four different groups, and that becomes a chiral carbon atom. And we know any chiral center if you have, right? They rotate the plane polarized light, right? Now, what do you mean by PPL? PPL is plane polarized light, right? So it is different from the normal light. Now, how is it different? Anybody wants to tell how normal light is different from plane polarized light? Sorry guys, I got a call. No, okay, so yeah, so what is the difference between normal light and plane polarized light?
So this light is produced by passing through the prism first, and then like furthermore, like it is passed through a compound which is capable of rotating the plane polarized light. That's how
I
it
understand.
works.
I understand. So that is the whole mechanism of it. So basically, you have the normal light, right? Normal light, right? You pass this to something called as a polarizer. Polarizer is what is your nickel prism, is what you're telling, right? They pass it through a polarizer. Then from this, you produce the plane polarized light, PPL. And this is given to a tube which contains your compound, and you are going to observe. You're going to put your eyes and observe from here what is going to happen to the output. That is the whole setup. What I'm asking is, why am I not using this? Why am I using this only? What is the difference is what I'm asking. The main difference is, guys, if it's a normal light, right? If it's a normal light, this is how I represent it, right? I put a round, one arrow at the top or one arrow at the bottom, or you can even put it like this, maybe if you want to, this thing. Okay, what does it represent is the photons. You know, light contains photons, right? Now the photons have the degrees of freedom. They can vibrate in all the three directions, is what you have to understand. One direction is along the y-axis, another direction along x-axis, and the round represents inside and outside of this plane. Into the board, outside of the board. Okay, so basically a plain polarized light, a normal light will have photons which can vibrate in all the three directions. Okay, now if it's a plain polarized light, what you will understand is you will see that there will be only one direction of vibration. Okay, photons can vibrate only along either of direction, x, y, or z, doesn't matter, but only one direction. Okay, so normal light contains photonic vibrations in all the three directions, and a plain polarized light contains, photons can vibrate only in one direction. Right now, because only then if they come here, only then if the compound is optically active. What do you mean by compound being optically active? Means compound capable of rotating the plane polarized light. Okay, so if someone asks you, what do you mean by an optically active compound? Right, an optically active compound is one which is capable of rotating the plane polarized light, either to the left or towards right, doesn't matter. But if it is capable of rotating, then that particular compound will be optically active. Right, so now the reason you see this is only one direction. Now you'll be able to easily sense whether it is getting tilted or not. Right, you will be able to sense whether, if you look at it, you'll be able to sense whether if you have all the three directions, something will happen and you'll not be able to get a clear picture. And that is why we go for plain polarized light. Okay, so we know, right, what kind of compounds can be optically active? I should have at least one chiral center. What is a chiral center? We know any compound which any carbon atom which has all the four groups to be different is a chiral carbon atom. And any compound which contains at least one chiral carbon atom is optically active. See, there are a lot of things connected here. Okay, what do you mean by an optically active compound? Is capable of rotating a plane polarized light. What kind of compounds can be optically active? The condition is that I should have at least one chiral center. And what is the next condition? For a compound to be optically active, one of the condition is it should have a chiral center. What is the other condition? Hope you understood my question.
Rotate plane polarized light, sir.
Yeah, that's what it should. If it has a chiral center, it rotates a plane polarized light, right? So I'm asking, for a compound to be optically active, one condition is it should have a chiral center. There is one more condition, not with respect to the rotation, something else. I think, I don't know whether they would have taught you. There should not be any planes of symmetry. For example, actually, I'm a little deviating, but it's okay. It's worth it, right? Say if I have this compound here, okay, do you have any chiral center here in this compound?
No, sir.
Look properly. Do I have any chiral center?
Yes, sir. Yeah.
How many? How many chiral centers are there?
2, sir.
Right, so you see this and this are the chiral centers. You see the four different groups: H, OH, CH3, and the entire group, this entire group. Same way for this carbon, H, CH3, OH, and this entire group. So basically there are two chiral carbon atoms having four different groups, right? Okay, now this has a chiral center, so this should rotate the plane polarized light, right? But what I see in reality is it is not actually going to be optically active, in the sense that it is not going to rotate the plane polarized light. Why? Because you see there is a plane of symmetry. In this plane, this can be divided into two exact equal halves, right? So whenever you have a plane of symmetry, right, the compound will become optically inactive. Okay, so two conditions for a compound to be optically active: one, it should have a chiral center; two, there should not be any plane of symmetry. If these two conditions are there, yes, we can call it as optically active. Okay, right? So being chiral and being optically active are not the same thing. For being optically active, one of the condition is having chiral center. The other condition for optical activity is going for the plane of symmetry. There should not be any planes of symmetry. Okay, cool. So why did I start all this? Is yeah. Tell me.
So which means like if the compound contains two chiral carbon, then it is not optically active.
Not
Can
exactly.
you
Say for
conclude like
example,
that?
if instead of this I had a C2H5, CH2CH3, then it is optically active. Do you understand what I
Oh,
said?
that. Yeah. So it only depends on the plane of symmetry and not on the number of chiral carbons.
Exactly. Correct. Right? If you're able to divide the compound into exact halves, even though you have whatever be the number of chiral centers, it is going to be optically inactive. But this case it will become chiral because this side and this side are not same, because this side I have C2H5, this side I have CH. Okay, cool. Good question. Fine. We'll move on. Oh, I rubbed it off. Hey, no problem. I'll draw it again. Right. So I have some carbon with some A, with some B, with some C, or I'll write it as, okay, fine, C, and then you have your X. Okay, now you're talking about SN2 mechanism, right? So now we know when the nucleophile has to attack from the side which is opposite to X, and that is obviously from this side. Again, you see nucleophile to the carbon center. That's what I'm writing. That's how I'm putting the arrow. Very important. Okay. So now how is going to happen? Now this comes here, and obviously this is a single step process. I'm going to directly write the product here, right? Now you see if this is going to attack from this side, this entire thing will shift like this. Okay. Now you see this is actually pointing towards something like this. It is right. If this is going to come and attack here, it is going to go like this. Okay, something like this. When something comes attacks, it goes like this to avoid repulsion. Okay, obviously. Why does it happen? Because to avoid the repulsion. VSCPR theory. Okay, we'll go into the details, right? So you will see that you have the B would have gone inside this side, and C would have come towards you, and you have the nucleophile attached to this side. Right. So this particular phenomena is what is called as
Inversion.
Correct. It's called inversion of configuration. Right. I have one configuration, right, that is exactly getting inverted. Why? Because the nucleophile attacks on the same side, opposite side. That is why the entire thing is getting ulta. Right. Now, please understand, you will be able to visualize the inversion of configuration only if the compound is chiral. Like if at all these three A, B, C are same, you will not find a difference between these two. Right. But you will be able to find the difference, the inversion of configuration, you'll be able to visualize only if the compound is chiral. Okay. Right. So that is about SN2. In SN2, what you have to understand is there will be inversion of configuration happen. Okay, cool. Now when I go for SN1, right, in SN1, we'll see what happens. So again, I'll take chiral center A, B, C. Are you able to see, right? Yeah. And I have the X, right? Now I know what is the first step. First step is removal of this X minus, right? So you have, now it becomes a planar molecule. Now, how it becomes a planar molecule? Now this is now sp3 hybridized. Right, this is sp3 hybridized carbon. Four groups are there. Now, if one of the thing leaves out, it becomes a carbocation, which will be sp2 hybridized. Right, this will be tetrahedral shape. Right, so there you will see A, B, and C. This is sp2 hybridized, and this shape is your trigonal planar shape. That means in the same plane, I have all the three bonds. And this and all is coming from your chemical bonding chapter, 11th class. Okay, if I have sp3 hybridized carbon, tetrahedral, sp2 hybridized carbon is trigonal planar shape. Right. Okay. Now what you have to understand is, people, the nucleophile has no restriction. right? Now, last time it had the restriction of being attacking only from the back side of wherever I had the halogen atom. Here, you see this is okay. This is a carbocation. I have to put a positive charge. Okay. Now, what happens? The nucleophile can come and attack from this side, or it can come and attack from this side also, right? So, what are you going to get? Right? What are you going to get? Is a mixture of two compounds. I would say a mixture of two isomers. And what isomers they're going to be? They're going to be stereoisomers. And special, I'll tell you, right? Okay, fine. So now you'll see that I have A. Now say if the nucleophile attached from this side, you will see exactly what happened here, right? You will have C coming here and B going away, plus if the nucleophile attached from this side, the same side of where I had the X. So the same configuration is retained. So you have A, you have B, you have C, and you have the nucleophile. Isn't it? Right? Okay. Now these two, what you understand is, guys, instead of this plus, if this was a mirror, right? Don't you see they are exactly mirror images of each other? Is it not? Right? They're exactly mirror images of each other, right? And they are non-superimposable. In the sense, you take it and you try to superimpose here, they are not going to superimpose. My hands will superimpose like this perfectly. But these two compounds, they are mirror images, but they are not going to superimpose on each other like this, right? Now, those non-superimposable mirror images are called as dash. Non-superimposable mirror images of each other. They're basically isomers. What is the name of the isomerism? I know it's stereoisomerism. Specifically what? Non-superimposable mirror images of each other means what? What is that called as?
Enantiomers.
Absolutely, right? So these two compounds are what are called as your enantiomers, right? So enantiomers are stereoisomers which are non-superimposable mirror images of each other. If you want to take down, please take down, right? Enantiomers are stereoisomers. You just see that the 3D thing is different, right? Whenever the 3D thing is different, they are called stereoisomers, right? Okay. So they are stereoisomers which are non-superimposable mirror images of each other. They cannot be superimposed. Even if they try to superimpose, they're not. Those are what are called as enantiomers. Okay. Now, what you see is that the nucleophile can attack from this side, or the nucleophile can attack from this side, right? Both with equal probability. There is no restriction that it has to come from this side only, or say there is no restriction that it has to come from this side only. There's no restriction, right? So both of them will be formed in 50-50% amount. Equal amounts of these two enantiomers will be formed, right? So what will happen now? I have a test tube which contains these two in equal amounts, right? Say assume that this is going to have D configuration. Do you know what is D? Right? D is dextrorotatory molecule. That means they will rotate the plane polarized light towards right. Okay, I don't know which is their right. This is my right. Okay, so what is that? The dextrorotatory molecules D configuration will rotate the plane polarized light by right, and we even give it as a plus sign, isn't it? We either D or right D, or we give plus, and the angle will also be plus. Say plus 30 degrees. It will rotate, assuming some random number. Okay, it is rotating the plane polarized light by 30 degrees. Okay, now if I come to this one, this is obviously, if this is D, that will be L for sure. This will be L, levorotatory. That will rotate the plane polarized light by the exact opposite way. Whatever be the quantity is same. So here it is plus 30. In this case, it will be minus 30 degrees. Towards the left, there it is towards the right. Correct, right? So what you see here, the net optical rotation is 0. Whatever is rotated towards the left is compensated by this molecule by rotating towards the right. Okay, right? Now this 50-50% mixture of enantiomers in the same test tube, that mixture is what is called as your racemic mixture, right? So if someone asks you what is racemic mixture, you tell them it's a mixture where the enantiomers are present in equal amounts. Enantiomers of the same compound, obviously, right? Enantiomers of the same compound are present in equal amounts. So racemic mixture's optical activity is 0. Even though you have two proper enantiomers, excuse me, since they are present in equal amounts, they are going to cancel the optical rotations of each. Okay, so stereochemical consequence of SN2 is inversion of configuration, and stereochemical consequence of an SN1 reaction is racemization or formation of racemic mixture. When I say racemization, is a process or phenomena or for forming a racemic mixture. Okay, so SN2 inversion, SN1 racemization. Now again, this will all will happen on and only if the carbon, the substrate molecule they're talking about is chiral, is having chiral. If not, none of these things matters. Okay, any doubts, people? Any doubts from any of these, from whatever we saw? I think I made it clear. If there's any doubt, you can ask me anywhere. Maybe even if it's going to be a little higher level than what is required, you can ask. No problem at all.
So clear, sir.
Okay, cool. So I think there's nothing specific, right, from this. Okay, fine. Now this is a good question. I'll ask you. Okay, so I have CH3Br and CH3Cl, right? Yeah, or CH3I, doesn't matter. Okay, CH3I. Okay, with respect to SN2 reaction, which reacts faster and why? Both are primary, you understand that. And tell me if for SN2 and SN1, for, oh no, SN1, okay, fine. SN2 alone will speak. Okay, which reacts faster and why? Okay, maybe we'll take a vote. Okay, I'll call 1, 2, right? Put it in the chat box, right? How many of you say 1 and how many of you say 2? It's just a guess game, and you might be right, you might not be right. Okay, so just put your answers in the chat box. 1 or 2.
So
Which
CS3I will be faster, sir.
Okay, put it in the chat box. So you're link 2. Okay, fine. Okay, so I'm saying everybody is giving 2. Where is the chat? Okay, so everybody is telling 2. None of you tell 1. Okay, fine, correct. Okay, the answer is right. Anybody wants to elaborate on why? Why 2 is more reactive? Again, you may
I'm
or may
not
not.
sure with the reasoning, but then I think because the size of iodine is bigger when compared to bromine.
Okay, so
So
okay, fine. I can take it as a partial answer, right? So
I
guys,
is better leaving group, like
yeah, that's the correct answer. I is a better living group, absolutely. Yeah, Aditi, correct. And someone, I don't know, what's your name, Kanna, now you told?
Anirudh, sir.
Anirudh, okay.
Anirudh.
So yeah, Anirudh and Aditi, both of you are right, right? It is because of something called as leaving capacity or leaving ability, whatever you want to call it. Okay, right? So what do you mean by leaving ability? As the name tells you, it is the ability to leave, right? So whichever has more leaving ability, right? Whichever group has a better leaving ability, that reaction would be faster, isn't it? Right? Okay. So for leaving capacity, there is only one criteria. Okay. The criteria is it is inversely proportional to the basic strength of the leaving group. Okay, not the compound. I'm not talking about the compound as a whole. Right now, the leaving capacity, talking about Br and I, which has more leaving capacity. Now that is dependent on the basic strength. It is inversely related to the basic strength. Right. So basically, a strong base, right, will be very tougher to cleave. Right. A weak base can be easily removed. Now, how do you decide the basic strengths is the next question. Right. Now that is very simple. Right. Now, hope you know the concept of conjugate bases and conjugate acids. Right. So can someone tell me what you mean? What do you mean by conjugate base of an acid? What do you mean by that? So if I have HCl, that's an acid, right? What is the conjugate base of HCl? Hmm? Okay, I suppose nobody knows. Cool. See, any acid HA, some acid is there, H and A is the anion. Okay. Now, what do you mean by conjugate base is after removing H plus, what is remaining? A minus is remaining. This is what is called as your conjugate base of the acid HA. Again, I repeat. After removing H plus, whatever is remaining, that is what is called as your conjugate base. So after removing H plus, in this case, I have A minus. So Cl minus is the conjugate base of HCl. F minus is the conjugate base of HF. CH3COO minus is the conjugate base of acetic acid. Okay, now I hope you understand. Right. Now, one more thing about what you can know about the acid and its conjugate base is if the acid is a strong acid, right, the conjugate base will be a weak base. Same way, if the acid is weak, the conjugate base will be strong. Ulta pulta. Strong acid, weak conjugate base. Weak acid, strong conjugate base. That's what you need to understand. Okay, right? Fine. So now I hope you understand why are we even talking about this? Because we're talking about basic strength, right? Okay. Now let me consider HF, HP, HCl, HBr, and HI. Now you have studied your P block, right? Arrange them in the order of acidic strengths. Arrange them in the order of acidic strengths. HF, HCl, HBr, and HI. Hey, the classes is for 1.5 hours, isn't it? Or 1 hour? Hmm?
1.5 hours.
Okay, 1.5 hours. Okay, fine. So Aditi says it's HF greater than HCl greater than HBr greater than HBr, HI. Okay. Anybody else wants to give any other answer? This is a very famous question from your group 17. And how do you not know this? I don't know. You wrote so many exams. You have at least had to prepare this chapter for 3-4 times. What is the order of acidic strength? Okay. So it is HI is the greatest than HBr, than HCl, than HF. That means HI is the strongest acid and HF is the weakest acid. At least can you tell me the reason for this? Why am I seeing this order? Why am I seeing this order? Think, right? HI is the strongest acid. Okay, stability decreases. Okay, why stability decreases? Obviously, because HI is the least stable. and that's why H plus can come out easily. Why Hi is the least here? I is electron. No, no. We go for electron
Bond
donating.
dissociation enthalpy, decrease in bond dissociation enthalpy.
Okay, right. It's correct. It's decrease in bond dissociation enthalpy. That means Hi has this very less amount of energy is required to break the bond. It's pretty much understood, right? H plus is a very small cation, right? I minus is a very big anion, right? So obviously, whenever you have the size difference to be very large, right, the bond is not that strong. Okay, the bond is not that strong. When the bond is not that strong, when the difference between the size of the cation and the anion is very large, a small cation or a big anion you have, right? So there, the bond strength is not so much. The bond is weak because you can say the overlap of orbitals are not happening properly. Okay, right? So that is the reason why Hi bond is the weakest. So I'll be able to easily take out H plus, and easier I get the H plus, more and more is the aspect strength, right? And say H plus a small cation, F minus a small anion, both of them will be very strong bond. H bond, and it is also stabilized by hydrogen bonding. Again, if you're interested, we'll speak about it later, right? So HF is the strongest bond, very strong bond, because the size difference is very small. Effective overlap is happening. So getting out H plus from HF is pretty difficult. That from Hi is very easy. Okay, now right. So this is the order of acidic strengths. Hi is the strongest acid, HF is the weakest acid. So if I take the corresponding conjugate basis, now only told you what is the conjugate base. Conjugate basis, after removing H plus, what is remaining, right? So in this case, F minus, Cl minus, Br minus, and I minus, these are all the conjugate basis of these four acids. Okay, now I told you that if the acid is strong, the conjugate base is weak. And if the acid is weak, the conjugate base is strong. Ulta pulta. Right? Now, can you tell me the order of basic strength for these four ions? From what you saw here, can you tell me what is the order? This is the order of acidic strengths. Now, these are the conjugate bases. Tell me the order of the strength of these conjugate bases.
So F minus, Cl minus, Br minus, I minus.
F minus is the greatest, I minus is the least, is what you're telling?
Yes. Yes, sir.
Good, right? So F minus is the strongest base, then Cl minus, then Br minus, then I minus. Is that understood? That's what I told you. Strongest acid, weakest conjugate base. Weakest acid, strongest conjugate base. So whatever is the order of acidic strength, the ulta will be the order of the basic strength of the conjugate bases. Okay, now why did we start all this question is answering this one, CH3Br, CH3I, which will react faster, right? I told you more and more leaving capacity, more and more is the reactivity, and the leaving capacity is inversely related to the basic strength. So stronger base is tougher to cleave, right? So among Br minus and I minus, Br minus is a stronger base, you see here, right? So the leaving capacity of I minus is greater because it's a weaker base. The leaving capacity of I minus is greater, and because Br minus is a stronger base, the leaving capacity of Br minus is little less, and the reactivity is also less. Okay, everybody understood everything whatever I said? You want me to repeat anything? See, in this one question, you don't have to write, like actually if you can write this much, wonderful, right? But at least you have to know leaving capacity. You have to tell that it is inversely to the basic strength, and you have to tell that Br minus is stronger base than I minus. That will be in the exam. Okay, any questions from this question? Like from everybody understood whatever it is? I hope it's clear.
Clear, sir.
Okay, good. Right. Fine. Next question. I don't want to ask you. Okay, fine. Maybe I will ask you. Okay. Fine. So I have CH3, CHBr, CH2, CH3, alcoholic KOH, A, then Br2 forms B, again alcoholic KOH forms C, right? And this C reacts with H2O, Hg2 plus and H2SO4 to form D. I wanted to find A, B, C, and G. So what does alcoholic KOH do when it comes to your alkyl halides? What do they do?
So elimination, sir.
Right? So they will form elimination. Elimination of HBr is what will happen. Right? Again, you have mechanisms for this, but not required. It is not the syllabus for you. Right? So again, you can form the double bond either between the first and the second carbon atom or between the second and the third carbon atom. Which do you follow? Which do you follow? Where should double bond be formed? Between first and second or between second and third? Between first and second carbon atom or between second and third carbon atom. Where should be the double bond be formed? When I put alcoholic KOH, major product is water.
So second and third.
Okay, why?
So more reactants should be attached.
There is just one rule which I'm expecting. What is the rule name? What is the rule name? So I say that the product is CH3, CH double bond CH3. Again, I'm just writing CH3 down. I don't have space. Okay. So you see, this is the major product. The other product would have been this. Right? Could have been this. Right? But I'm telling this is the major product. This is the minor product. Why?
According
So
to
more
Markov
alkyl-
rule.
Markovnikov's rule is for this or something else?
So
Markovnikov
more
is
alkyl group. More alkyl
more
group.
alkyl group. Okay, okay, I understand. That is, like, coming to that. What is the name of the rule? Ma'am, Markovnikov's rule is for addition of HBr. Right? That is for addition reaction. Elimination reaction, there is one rule. What is the rule? The reason you said is correct, right? I have more substituted. Basically, when this alkene, when I compare it to this alkene is more substituted. In the sense, the double bond C carbon is attached to two other carbon atoms. This side one carbon, this side one carbon, right? But here, this carbon are attached to two hydrogen atoms, not so much substituted, right? So that is why generally substituted alkenes are more stable than unsubstituted alkenes. That is the reason. But what is the name of the rule is what I'm asking. Really, guys? Okay. I don't know. You must have seen this. States of rule. Does it ring any bells? Yes? No? Was it taught? Sides of rule? Correct. Aditi says yes. Right? I hope like it should have been taught. How will they not teach this? That means you only are not remembering. That's the obvious fact. Right? So sides of rule says that a more substituted alkene should be formed in case of an elimination reaction. Okay, fine. So A we found out that is a major product. Okay, fine. Now what happens when I add Br2? Hmm? What happens when I add Br2 to the alkene? Come on, guys, you have to be really fast. What happens? I have a C double bond C.
Addition reactions.
That's it, right? That's simple, very simple. The Br bond is going to get attached to these two carbon atoms. That's it, right? So you will see this is A. A is the sides of product. So B, right? So B would have been CH3, CHBr, CHBr, CH3, right? So across the double bond, you add two Brs, right? Okay. Again, alcoholic OH, what will happen? Elimination. Okay, elimination I know is going to happen.
Yes,
What will be the
again,
product? Sorry?
yes, sir. Like again, elimination will occur. That's all.
What will be the product? What will be the product? I have two Brs, and if I put alcoholic OH, what will happen? Last time you had only one, so you formed an alkene. This time you have two, so you will form alkyne. Good. Yes, you are going to form alkyne. So one Br and H double bond, one Br and another H triple bond. So you C is basically going to be C triple bond C, CH3 and CH3. This is what is C. Easy, right? You have one Br and alpha hydrogen. You remove beta hydrogen. You remove them to form an alkene, right? Now you have two, so you remove both of them. That is both H2, one HBr, second HBr. You remove to form this CH3, C triple bond C, CH3. Okay, what is this reaction? Hmm? What is this reaction? Tell me. H2O, Hg2 plus, H2SO4. What, like say if at all I had a double bond, and if I'm going to put this here, what will happen? What is the name of the reaction first? Oh, this is not oxymocration. This is different. Actually, yeah, this is oxymocration and democration. This is oxymocration, democration, right? Alcohol, phenols, ethers chapter. Oxymocration, democration. So please understand, when you have a double bond and if you're going to put this complex H2O, Hg2 plus, H2O, H2SO4 and all that, please understand it is equivalent to just adding a water molecule. That's it, right? This is equivalent to just adding a water molecule. So what will happen is you will form COH and this is going to have a H. That's it. Now this happens if I have a double bond. What will happen if I have a triple bond? What will happen if I have a triple bond? What is the only difference? Here you add water molecule. There also you're going to add water molecule. But how many? Here it is one. So there it is. How many, guys? How many water molecules? Here it is one water molecule because there's only one double bond, pi bond. Here I have two pi bonds. So obviously I have to add two water molecules because when you have an alkyne, right? So please remember this. when you have C triple bond C, and when you're going to use this one, H2O, Hg2 plus H2SO4 and all that, right? You are going to understand that you are going to have two OH groups of the same carbon atom again because of Markovnikov's rule. Okay, we'll come to that. Markovnikov's rule says that the nucleophile has to attach itself to the carbon atom which is more substituted. How many ever times you do it? Either you do it one time or whether you do it two times. That carbon atom which is more substituted only will get the nucleophile. So here the first nucleophile OH like this carbon because it is more substituted. Same thing again will happen on the same carbon atom because it is more substituted. Markovnikov's rule. Okay, so now I have H, and the other one. That's it. Okay, so here you added two water molecules. So OH, OH, H. Now what? There is something wrong with this compound, right? What is wrong with this compound? Do you know that is unstable? This kind of compounds are unstable. Do you know that? Why? Okay, guys. Please understand that when you have two OH groups on the same carbon atom, it is unstable. Please remember this. Okay, they are unstable because of lone pair repulsions. Both the oxygen atoms will have lone pairs, right? So it is really unstable. So what will happen the moment you form a carbon atom having two OH groups, right? You can easily remove a water molecule. H from this, OH from this, you remove it. So you will form C double bond O. Okay, please. This can be used wonderfully in terms of conversions, right? When you're going to go for conversions, right? This will be very, 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 very useful. Okay, you attach two OH groups from same carbon atom somehow, and then you can easily remove water molecule to form an aldehyde or a ketone. Okay, now see, that is what is exactly going to happen here, right? Can you not see? You will have this one CH3 C OH OH C H CH3. Is it not? Two water molecules getting added, right? So what is going to happen? I am going to remove a water molecule, so you'll form CH3 CO CH2 CH3. This would have been the product D, right? So D is this CH3 C double bond O CH2 CH3, right? Now everything else you know, then maybe the only thing which you don't know here is this. Right? So whenever you have H2O, He2 plus He3H4, assume that it is just addition of water molecule, addition of H2O. If it's a double bond, one H2O. If it's a triple bond, two H2Os, and both the OH groups will go to the same carbon atom like this. And then I told you it is unstable. Remove the water molecule to form the aldehyde or ketone. In this case, it's a ketone. Okay, everybody understood the problem? Yes. I want everybody to tell me yes if you understood. No means no. Yes, everybody understood?
Yes.
Yes.
Okay. Okay. Fine. I hope there are no problems. So a lot of things again you studied. What is the time? Okay. So we have 3 more minutes. Maybe I'll stop. Right. So guys, please do practice all your NCERT book back. That's the best exercise you can do for any chapter for that matter. Right. Just solve the NCERT book back exercises, and you if you find in Google, you will find answers to all the questions. Or obviously you have your faculties, you have me, you have Raghav, right? You can ask any of them, right? So you'll be able to clarify this. Okay, so let's see in this particular chapter, right? The mechanism is very important. Zaitsev rule is important. Markovnikov's rule is important. Right? So all these things you have to use it, right? We maybe if at all from next chapter we'll anyways do a lot of reactions. At that time we'll include reactions of this also. We'll do conversions, we'll do problems like this ABCD problems, and we'll do a lot of conversions and some theory questions from next chapter from your all the other organic chapters, alcohol, ethers, phenols, aldehydes, ketones, carboxylic acids, right? So amines, all these things, right? We'll do only 2 types of questions from now on. This ABCD type of questions and conversions, and about the reactivity, why this is more reactive, why this is less reactive, right? Those kind of questions we will solve. Okay. So guys, I think for some of you, this might be the first class. Is my speed okay, or any other problem you face? You want me to change anything? Is there any problem?
Yes, sir. Perfect, sir. No problem, sir.
Okay, no problem. Fine. Cool guys. I don't know when is the next class. I think tomorrow is the next class, I suppose. So tomorrow
Yes,
we
sir.
will see.
Tomorrow's the class.
Good. Right. So tomorrow we'll see alcoholic phenols, and don't worry, we didn't see all the reactions today, but we will incorporate all the reactions in the tomorrow's class. Anyways, the reactions will repeat when you go to alcohol. Okay.
Sir, I have
Fine.
a doubt. I have a
Yeah.
small doubt.
Yeah.
So on adding alcoholic KOH first, there is
Hmm.
HBr being moved, 1 molecule of HBr, and
Good. Yeah.
again like in the third step or something, again we are adding alcoholic KOH. There we are
Correct.
removing 2 molecules of HBr. So
Yes. Correct.
so which means like if we keep on adding keep on like adding the alcoholic KOH and Br2, then like all
You
the
see,
HBr will be removed or something like
yeah,
that.
how much ever possible you will be able to remove, but please understand, between two carbon atoms, the maximum number of bonds possible is only 3. You cannot form 1, 2, 3, 4 bonds between carbon. This is impossible, right?
Yes, sir.
So
Yeah.
by theory, what we're saying is correct, but again, you cannot form more than 3 bonds between the same carbon atom. That is a limitation there. That's it. You have to stop with that. Yes, understood. I think I answered your question.
Yes, sir. Yes, sir. Okay.
Okay, good. Any other questions?
Sir, and I had
Yeah.
one more thing. Like,
Yeah.
it's in the NCRT example. I couldn't understand that.
Tell me.
It's like the chlorine is an electron withdrawing group, yet
Hmm.
it is ortho para directing in electrophilic aromatic substitution.
Yes. That's a good question. Okay. So, guys, if you this is a nice question. If anybody wants to stay, they can stay, or if you want, you can leave. Okay. Right. So I have chlorine here. Okay. Right. Now, what you have to understand is chlorine, as they say, is actually by inductive effect. Right. By inductive effect, chlorine is actually an electron withdrawing group because it is highly electronegative in nature. I understand. Right. But if I go to resonance, please understand that this has lone pair here. Chlorine has lone pair. So the resonance structures will actually start from the lone pair coming here and this bond breaking. Right. So you have to show the resonance structure. Now you will have double bond Cl plus. Right. Now you see there is a negative charge formed here because this bond broken and came here, and the other bond stays. Right. And if you look at the next one, the negative charge will form a double bond here, and this bond has to break. Right. The next step would be double bond Cl plus a bond formed here. Right. And this bond came here. Oh, basically, I can put it as a negative charge. This comes to this card, and there is a bond here. Okay, I'll change the marker once again. So there is a double bond here. Right. Now what will happen? This will go and this will go to this carbon. So you will see that double bond Cl plus a double bond here, a double bond here, and negative charge here. Last step is this will come and this will go back. So the last step would be a bond here, a bond here, a bond here, and a Cl. And the positive charge is gone because the bond is going back to chlorine. Right. Okay. Now you see what they're asking is, even though chlorine is electron withdrawing group in an electrophilic substitution reaction, this is like basically in benzene will undergo only electrophilic substitution. Okay. In an electrophilic substitution, even though it is electron withdrawing group, it is ortho para directing. Is because of the resonance structure. You see, an electrophile, a positive charge is going to attack the benzene ring. Right now, that attack will happen wherever I have negative charges. You see, the negative charge is formed here, negative charge is formed here, negative charge is formed here. Only in ortho and para positions you have the negative charges formed. And so the incoming nucleophile will attack only in the ortho and para positions and not in other positions. Right. If if it was a normal electron withdrawing group by resonance. See here, chlorine is electron withdrawing by inductive effect, but by resonance, it gives plus R effect. Plus R effect means it donates electron to the benzene. That is the reason, right? If it was anything like NO2, nitrobenzene, right, which actually gives me minus R. So how will I prove it to you? I have N double bond O minus. Now first, there is no lone pair on nitrogen here. The first step would be this bond going here and this bond breaking. So you see, this carbon atom will get a positive charge, right? So whenever you have electron withdrawing groups present, right, you will have positive charges formed here, here, and here, right? So what is going to happen? The electrophilic substitution, if I go to an electrophile, it cannot attack in ortho and para positions because I already have a positive charge. So it will try to attack the meta positions, which doesn't have any positive charge. Okay, so whenever you have groups which are going to give minus R effect, they will be meta directing groups, right? Whenever you have something like chlorine, which is actually a special case, minus I it will give, and plus R it will give. That's a special case with respect to chlorine. And that is the reason why it gives me ortho-para directed products. Okay, understood?
Yes, sir. Yes, sir.
Okay, any other question anybody has? Guys, whenever they ask you this question, it's better you draw the resonance structures and show why it is ortho-para directed. Because you see the negative charges are found only at the ortho positions. Right? Okay. Any other question specifically from NCERT? Any question you saw somewhere in your exams, in your NCERT, some test you are not able to answer regarding this chapter, you can ask me now. Okay. I suppose there are no questions. Okay, guys, we'll meet you tomorrow, same time, 6 o'clock. Right? We'll discuss alcohol ethers and phenols. Okay. Thank you so much. We'll meet again.
Thank you, sir.
Yeah.
Thank you, sir.